we've seen the quantum one-time pad. And to understand how the quantum one-time pad works exactly, let's now consider a very simple example. In the lecture notes, you can find a more complicated one. The qubit that I want to encrypt here, psi, is just the plus state. And remember, we want to know what is the state that Eve sees, and Eve does not know the key. So we want to compute the density matrix, where we sum over the key bits, K1 and K2, put here 1 over 4, because there's 4 possible keys, they're all equally likely. And depending on the key, the state is as follows. So let me now compute these 4 cases separately. So there's 4 possible values for the key, starting with 0, 0. So 0, 0 is very simple, because in this case, we just keep the state psi, which is plus. So we've computed this a few times, and we get that this is half times 1, 1, 1, 1. Let's now consider the case where we just apply x. So we've seen that x does nothing to the plus state. So here we again just have plus. 1, 1, 1, 1. Let's now consider what happens if we apply z. And remember that z is the bit flip in the plus-minus basis. It takes plus to minus. And if we compute this, get 1, minus 1, minus 1, 1. So finally, we have to consider the case where we apply both x and z. We can easily compute this by considering this case, and now we need to apply x. So I've already computed what happens if I apply z, so now I just need to compute what happens if I also do x. So remember that the only thing that x does to the minus state is it adds a minus in front, a phase. But for density matrices, this phase doesn't matter. So what we get is exactly the same thing as before. 1, minus 1, minus 1, 1. So let's now compute what this average state up here actually is. If I plug in these 4 cases, we see that we have overall factor quarter in front. We have 2 times half 1, 1, 1, 1 from these 2 cases here, plus 2 times half 1, minus 1, minus 1, 1 from these 2 cases down here. So if I compute this, what we'll have is a quarter, 1, 1, 1, 1, plus 1, minus 1, minus 1, 1. So if I add these matrices, what we'll have is a quarter. 2, so 1 goes away against -1, 0, 0, 2, which gives me half times the identity matrix. So we see that for our example, we got, as expected, the maximally mixed state. Eve sees the maximally mixed state independent of the initial state plus.